Hi everybody, I'm going to talk about Fischer and Haworth projections in this video. So it's just going to kind of go over how to interpret a Fischer projection and how to go from Fischer to the Haworth projection, which is that cyclic structure. So the Fischer projection is a really common method of drawing sugars, or just drawing anything that has a lot of stereocenters, because it's just a way of kind of organizing them so that it's easier to look at, but unless you know what they mean, they can be a little bit tricky. So when you're looking at a Fischer projection, you want to keep in mind that any intersection carbon is a stereocenter. Okay, so if two lines are crossing, that means you've got a stereocenter at that carbon. And the way that you want to interpret this is you want to think about it in terms of wedges and dashes. And it's a little bit awkward, but you're thinking about it instead of kind of how we usually look at things this way. We're basically kind of turning that so that we're looking at it. Just let me pause real quick. I need a model. Alrighty, I got my model. So we're really looking at it in terms of, instead of kind of looking at it this way, where we have some stuff in the plane, some stuff going in and out. What we're looking at it is we're more looking at it like this, where we're kind of looking here. And actually, yes. So where the stuff that's going up and down is going on dashes away from you, and the stuff that's on the horizontal is going towards you. So it's just looking at it from a slightly different perspective, but we're still looking at the same thing. So the way that we want to interpret it is we're really looking at it as that carbon in the middle, and then anything that's on a vertical is on a dash. So our ethyl and our methyl are going to be on dashes, and anything that's on horizontal is on a wedge. Okay, so that's essentially what we're looking at for any Fischer projection. It's just a slightly different, viewpoint compared to what we normally have looked at. All right. Okay, so we're looking at, we just kind of look at some options here. The other thing that Fischer projections can help you do is they can help you identify stereoisomers pretty easily. Okay, so if we have something like this, we can draw the enantiomer of it pretty quick. Okay, so these are enantiomers. If we look at another example, okay, these would be diastereomers. And then we can also identify if things are achiral pretty quickly. Because if we have something like this, we do have stereocenters here, but we also have a plane of symmetry, right? We've got our mirror plane right there. So this is going to be achiral. And that is really easy to see the plane of symmetry there, because everything's like flattened, right? So we're still identifying like, yes, we do have stereocenters, but everything is flat so that you don't have any of those wedges and dashes that you're looking at. And remember this one, because it is particularly, does have stereocenters and is achiral, this would be an example of a meso compound. So one thing that Fischer projections can kind of make a little bit challenging is assigning R and S on them, because it's tough to assign R and S when you have two wedges and two dashes, and then it's just a little bit tough to tell what's going where. So assigning R and S, there's a little trick to it. Okay, so what we're essentially going to do is we're going to take our Fischer projection, Okay, and we're going to keep in mind that, yes, we do have, you know, the wedges, we have the dashes. We're going to convert it to the structure that we're more comfortable with working, right? So we have two things in the plane, one thing on a wedge, one thing on a dash. So the first step is we want to draw one of the horizontal lines. Okay, so one of the sideways ones that are wedges, and we're going to draw it as a wedge. And then we're going to draw one of the vertical lines as a dash. Okay, I think it does help a lot to be a little bit strategic with this process. If you do it strategically, you can make sure that you put 4, whatever your listing is for, on a wedge or a dash. Okay, because we want to always keep in mind that having your least high ranking like substituent on your stereocenter, we don't want that to be in the plane, because then we're gonna have possibly like 50-50 chance of being right. So the first thing that I would do when we're looking at assigning the Fischer projection, let's just go ahead and do the 1, 2, 3, 4 assignments first. So this is going to be just like a normal RS, where we're saying carbon versus nitrogen versus carbon. So nitrogen is going to win that. And then we've got carbon with 1 oxygen versus carbon attached to basically 3 oxygens. So then we've got 2, 3, and 4. So once I have my assignments, then let's go ahead and do steps 1 and 2 here. So I've got a carbon. I'm going to put my H, which is number 4, on a wedge. Remember, horizontal is on our wedge, which means that my NH2 is just on a line. And then I need to either pick 2 or 3. It does not matter which one. Okay, the most important one is just making sure that your number 4 is on some kind of wedge or dash, so you know that you either are just keeping your counterclockwise, clockwise the same, or whether you're switching it. And then the other side is just going to be on a line. Okay, so now we basically have it here, except we just have it kind of tilted a little bit. But now we have 1 wedge, 1 dash, 2 in the plane like we're used to seeing. So now we can go ahead and add our numbers again. Okay, we want to keep in mind that our number 4 substituent is on a wedge in the front. So whatever we get, we're going to need to flip it. So I'm going counterclockwise here. But the H is in front. So this is going to be R. Okay, so it would be S if we were just sticking with counterclockwise, but because that H is there, we're going to switch that to the R instead. So this you would just do for each stereocenter individually in a Fischer. Okay, so for each chiral carbon, you're basically looking at that carbon and then the 4 things that it's attached to, and just taking it apart one by one to do that whole like 2 in the plane, 2 out of the plane type of situation. So it can definitely be a bit of a laborious process to go from Fischer to R and S, but it is a good thing to be able to know. All right, so then let's look at Fischer going to the Haworth projections. Okay, so we want to just keep in mind here, we want to keep ourselves focused on what chemistry is actually occurring here. This is just a hemiacetal formation. Okay, the tricky part is really just dealing with the stereocenters and the Fischer projection itself. Okay, so keeping ourselves focused on what we actually have, that's going to be really helpful. A couple things to note here, this about sugars in general. So you'll see D or L sugars a lot, and this is like D as in dog and L as in lamb. So D sugars are the naturally occurring ones. Okay, so naturally derived, and they always are going to have the OH closest to the CO2 OH. That's going to be on the right side. Specifically in the Fischer production. Okay, so if we're looking at D-ribose, for instance, 1, 2, 3. Okay, so we pretty much always have one end that has a carbonyl, like a ketone or an aldehyde, one end that has the CH2OH, and then we're looking specifically at this OH right here. That being on the right-hand side is what makes that a D sugar. So this one is going to be D-ribose once I finish drawing it in. So that has OHs all here. Okay, if we look at glucose, this is going to have 4 stereocenters. Okay, so then we have this is D-glucose. And we're specifically, again, looking at this H, this OH. This is the important one for D. All the other ones can kind of be wherever they want, but you're specifically looking at that D, okay? Then when you go to the Haworth projection, okay, for the D sugars, when they're in that cyclized state where we have, I think it's usually this one that's going here. So we have 1, 2, 3, 4, 5, 6. Yep. So when we're in that pyranose form, which is what they call that pyran, like 6-membered ring with an O in it, for any of those D sugars, we're looking at that CH2OH going up. Okay, so D is going to have that CH2OH up. Okay, so then the next thing that we want to note is you'll see the D and L annotation. We'll also see the alpha or beta. And that indicates the stereochemistry at the anomeric carbon. Okay, anomeric is just a fancy word for the hemiacetal carbon. Okay, remember that hemiacetal carbon, it used to be your ketone or aldehyde carbonyl carbon. Okay, so when we're looking at alpha, that's going to be, the OH is going to be trans to the CH2OH. Okay, and this is the OH on that anomeric carbon. Okay, if we have beta, it's going to be cis to it. So when we're looking at an example here, we'll look at beta D-galactopyranose. Okay, so this is originally starting with D-galactose, which is in its acyclic form. Okay, and then this bottom one, we're specifically saying, okay, if I've got a D, I'm going to have my OH over here. And then I've got my CH2OH. And I've got H's in all these other ones, these other spaces. Okay, so when I go to my Haworth projection, we always draw the ring this way. You'll never see it drawn any other way. So it's always going to be the O in the ring is in the back right corner. If I'm looking at beta here, so my anomeric carbon is this dude. Okay, so if I've got a beta, oh, I guess I need to put this one in first. Okay, so if I have the D, that means I'm going to have my CH2OH up. Okay, if it was L, it would go down. So that means if I'm doing beta, I need to have it cis. So that means this OH needs to be going up. So this H is going down. So then we've got this is up. This is up. These two things are cis. Okay. And then when we're looking at the rest of this, because we still have all the other OHs to put on this ring, and let's just go ahead and do a little bit of numbering here. Okay, so that carbon 6 was our aldehyde carbon, so we're going like, woo, that. So when we're looking at where do I put the other OHs on carbons 3, 4, and 5, then I'm really looking at any of the OH groups on the right side of the Fischer. Those are going to be going down in our Haworth projection. And then vice versa, any of the OH groups on the left. Those are going up in the Haworth projection. Okay, so we're looking at this side, we're going up. This side, we're going down. So if I'm looking at carbon 3 here, I've got one up and one down. So I've got an OH on the left, so that's going to be up. So that H is going to be down. On carbon 4, I've got an OH that's going up, H that's going down. Oh, wait. Yes, okay. And then on 5, I've got an OH going right. So that one's going to be down, and my H is going to be up. Okay, so then that's going to be our beta D galactopyranose from our D galactose. Okay, so we're just equilibrating between these two, basically between the open chain and the closed forms. Alrighty, so hopefully this was helpful. Fischer projections are not going to feature super heavily in class, but if you run across them, I want you to be able to understand what they're actually trying to say to you. But really, we're just going to kind of keep it like, think about it with the wedges and dashes, and it's hemiacetal chemistry, and that you're going to be okay. Alrighty, let me know if you have any questions, and I'll see you all later.